This short movie introduces Compsim's KEEL technology as it applies to the goal-seeking policies of unmanned combat aerial vehicles or UAVs. KEEL stands for Knowledge Enhanced Electronic Logic. This video also provides a backup introduction to the UAV demonstration on Compsim's website. KEEL technology provides a way to capture, test, package, audit and explain human-like reasoning, such that KEEL cognitive reasoning components can be deployed in devices like UAVs or in software applications, such as simulations or electronic games. This will then allow those applications to exhibit the same judgment and reasoning skills. Reasoning is different than conventional information processing using if-then-else logic. Reasoning requires the information sources to be valued under continuously changing situations, and alternatives to be balanced against competing goals. In humans, this is commonly referred to as a right brain process. It is more of an image processing function, where valued information items are processed and balanced collectively, rather than processed sequentially. More right brain than left brain. This is a key differentiator between KEEL technology and conventional rule-based systems. It is effectively an analog process, where KEEL packages analog processing functionality in a manner that can be executed on a digital computer. In this case, KEEL cognitive engine components are deployed in simulations of UAVs. The KEEL engines provide the policies that controls their behavior. You will see two UAVs in this simulation. Each is processing the same policy, but operating with full independence. Some of the information processed by each UAV is shown in the upper right corner of the display. Information boxed in red is for UAV 1. You will note the red wings of UAV 1. Information boxed in yellow is for UAV 2. UAV 2 has the yellow wings. Human control is offered by allowing the human commander to change how the UAV thinks, not by exerting absolute remote control. This is provided by the mission control slider in the lower right. This allows the UAV to take advantage of what it knows, in addition to what is contributed by the remote field commander. And remember, the UAV knows the real-time information because it is there, operating in real time. The remote commander may have access to more strategic information. The objective of both UAVs is to find and engage the target, which is shown as the larger red dot on the screen. The target has both an observed target value and a perceived risk associated with attacking the target. The UAV does not know the value of the target, nor the risk, until the target is detected and identified. The UAVs fly random search patterns as they scout for the target. Smaller red dots indicate defensive sites, that can shoot at and damage the UAVs. The UAVs cannot see the defensive sites until they are very close to them. If a UAV detects a defensive site, it may make an evasive maneuver or it may attempt to hide if there is sufficient cloud cover. In this demo, there are no simulated clouds. The KEEL-based policy tells the UAV how to balance between making an evasive maneuver and attempting to hide when a threat is detected. The UAVs constantly monitor their health, their fuel supply, and their weapon supply as they fly their mission. In some situations they may decide not to attack the target when it is identified. This is because they are integrating the risks and rewards as defined by their KEEL-based operating policies, or rules of engagement. So if the UAV identifies a target and rejects the engagement, it has decided that the target's value was not sufficient to offset the risk based on its present operating status. In this demonstration we have also integrated the human emotion of frustration into the goal-seeking model. Frustration is a human characteristic that helps humans try different approaches to achieve goals, when one strategy fails. It is used here so a UAV will not continue to pursue the same unsuccessful strategy, while attempting to find a safe way to engage the target. You will observe the two UAVs flying on the map. By default they are flying to random points searching for the target. However, by clicking on the screen we can direct UAV 1 to fly to that point. Shift-clicking causes UAV-2 to fly to another target point. No keel logic is applied here, except that as the UAVs fly around they are each utilizing their own fuel supply. Fuel supply is one of the items that each UAV monitors constantly. In the upper right corner of the display, you can see the fuel supply gradually being depleted. We can attempt to get the UAVs to collide, by selecting conflicting flight paths. The respective keel engines each tell the respective UAV how to avoid the collision. Note the evasive maneuver as the UAV flies over a red defensive site. Also note the damage that the UAV incurs as it sustains incoming fire. This is shown by the flame coming from the UAV, and in the information box in the upper right corner of the display. The outer ring around the UAV indicates the range where it can detect the target. It tries to find a safe way to attack the target. Once it starts an attack, it balances risk and reward to determine the optimal instant to fire its missile. We have two canned scenarios that allow us to demonstrate the use of frustration in the policy that describes how the UAVs are to behave. In this first case, the UAV eventually finds a safe way to engage the target. In the upper right corner of the display you can see its frustration increase. But in this case it finds a way to successfully complete its task before frustration takes over. In the second case, we add another defensive site. Now you will observe that frustration increases as the UAV attempts to find a safe way to engage the target. In this case frustration, according to its rules of engagement, takes over and the UAV gets frustrated and goes home. You can monitor this process in the upper right corner of the display. Now we will run the first pattern again, but now we will change how the UAV interprets the scene. We will use the mission control adjustment in the lower right corner of the display. Here we are simulating information from the field commander or from some other information source. By sliding the scroll bar to the right, we are telling the UAV that the target is more important than it might think it is. And we are telling the UAV to be more risk tolerant. In this way we are able to influence the behavior of the UAV in order to get it to do what we want it to do. We are changing how it thinks. But we are still allowing the UAV to use what it knows of its own status, in order to make the final decision. For example, if the UAV was damaged to the extent that it could not complete the mission, or it didn't have any weapons remaining, it could still reject the mission. In this case, we have made a mission control adjustment, and even though the UAV senses a defensive site thus increasing risk, it proceeds to engage the target. Once it engages the target and fires its missile, it heads home for refueling, repair, and reload. The KEEL-based policy controls how the UAV integrates external and internal information. The human that creates the operational policy is in control. The UAV is able to adapt to changing information at any time and still perform according to the human-generated policy. You can interact directly with this demonstration on Compsim's website at www.compsim.com. Check out this demonstration and several others in the demos area.